nice visualization about the activity, but how come, matlab, we need to think then, but what you will be doing with the size of the craters?
Just a question, sir. I was just asking if we can apply this on that. That's it.
नहीं, ठीक है मतलब somehow we can create a model that satisfy our need. ठीक है, we can think about it, we can talk. Okay, so I hope the screen is visible and my voice is clear, and I think good evening and welcome back to the session for GNN. Just want to check whether the screen is visible and my voice is clear. Please confirm.
Yes, sir.
Yes,
Okay,
it's
chalo. So quickly, let's start from where we have left in the previous session. So we were covering the page rank. So let me connect all the all the things that we have studied right from the beginning. So basically, ultimately, when we start with this module of network measure, our intention was to come up with certain numbers or some numbers which gives me more information about the connectivity of the graph, how you are connected to others, how others are connected to you, and many other things. So some values associated with each node or with each edge with respect to the neighborhood of the node. Okay, so in neighbors or out neighbors, in either way it can be in anything. So the first value that we thought of we can come up with an assign a number was based on the degree. So we call it as degree centrality measures. So that purely based on the number of neighbors, in neighbors or out neighbors we have. And then we can normalize it, and we can fix them in certain range, but we can assign a particular number to each node based on its own size of the neighborhood. Okay, either in neighbor or out neighbor. Then that degree centrality was having an issue. Okay, the thing is that for the degree centrality, all the neighbors were same. Fine. So we changes from degree centrality. We move from degree centrality to eigenvalue centrality. So in that case, somehow we try to figure out that more important nodes should be given more importance and less important nodes. So not only degree, the importance of the neighborhood also should play a role. Fine. So we move towards the eigenvalue centrality. Eigenvalue centrality has an issue. We come up with that issue that in a directed graph, whenever we encounter a directed acyclic graph, the eigenvalue centrality will become 0. So in that case, if it becomes 0, then in that case, it will creates a problem for us. So what we did was we assign a small positive number to so not assign, we add a small positive number to every node of a graph, to the importance of a graph, so that it ensures that it is always greater than 0. It is always some positive value. So we call it as a curve centrality measures. Then that curve centrality measure was also key. We take care of the we should not pass all our importance to all our neighbors equally. We should pass them proportionally. So then we come up with the next centrality measures. We call it as page rank. So page rank means now here the complete importance is not passed to the neighbors. Only the proportional based on the out degree of that node is being passed to the neighborhood node. So fine. So that was the next version of measures, network measures was, which call it as page rank. So that means PageRank algorithm was one of the, we can say, updated version of all the network measures that we have looked so far. So this is the whole connectivity right from the degree centrality, degree to the importance of a node. Okay. Then we come up with a method, but the process of calculating the page rank was, in terms of mathematics, it may be computationally intensive. So we thought of, so someone come up with an idea of of updating the page rank in an iterative way. So they suggested some method and they call it as power method, and somehow they calculate the page rank. Okay. Now, if you want a working example, one different example, so I also have solved it on the same traditional graph. Okay. So what we did is was, okay, based on the graph, okay, directed graph. This is our directed graph, and based on that, we we computed, or we performed the iterative method for page rank. Okay. So initially it was, as it has 10 nodes. So initially all of them was having 1 by 10. So zero point 0.1. So there was 10 node, zero point 0.1 to each. So that means total overall page rank was 1. But for the second iteration, we compute the, we come up with the formula for page rank, and that is specific to node. So this is the one pre-processing that we will have to do before executing the page rank algorithm on any of the node. Okay, so that means A receives the page rank from D, which is P5. Okay, which is D, and how much part of a D? Half of it. One of the out neighbors of D is A, and one of the other out neighbors of D is J. So A receives his page rank from D, half of D. Similarly, B receives its page rank from two of the node, from A as well as from the C. Half of, sorry, one third of A, and one and one third from A, and half of C. Okay, because C has two outgoing neighbors, so half of C, and so on. Okay, so we compute the formula. Okay, we come up with the formula, and then using the latest value, okay, we come up with the updated page rank for iteration 3. Second, sorry, iteration 2. Total sum of iterations, total sum of all the page rank is still is equals to 1. So initially in the first iteration, the page rank of A was 0.11 by n. Now it was updated to something else, 0.05. Okay. For some cases, it has decreased. For some cases, it has increased. Okay. So this we were capturing. So this we have captured the difference in the page rank in a separate matrix. So this matrix scores or stores the change in the page rank per iteration. Okay, so that means at this is the change in the page rank from page rank of B from iteration 1 to iteration 2. So some changes are positive, some changes are negative. Okay, so now the moment we can say the criteria for our convergence will be, okay, if that change of page rank in each iteration, if it is below some threshold, we can say our population has converged. So if that change is, suppose, around 0.005, okay, so if the difference, the change in the page rank is below the threshold of 0.005, we can say our population has converged, and that will be the page rank of that node. So this was the page rank at the second iteration. So similarly, if we have to find out the page rank for third iteration, it will be using the page rank of the second iteration. Okay. Similarly, page rank for fourth iteration will be using the updated page rank for iteration number 3. So that means if we are computing the page rank 6, the only thing that we require is the adjacency matrix, Based on that only, we will be computing the for formula, and the page rank, the last iterate, we can say the previous iteration page rank, or we can say the latest page rank so far. Okay, so this is what we require, and we move, or we move from one iteration to the other iteration until all the all our termination criteria match. So if our termination criteria is that if all the values are lesser than 005, okay, 0.005 absolute value, does it work? Absolute function works over here? 9. Okay, 0.005. So now you can see in this, many was 0.005, many were lesser than 0.005. Okay, so until unless, so in this case also, uh, if we have to come up with certain absolute function, then I think it will be good, even positive and negative. But suppose this difference will not work. Greater than 0.005, we'll have to highlight all the values which are greater than 0.005, okay, and which are lesser than minus 0.005. This sounds good. So if our criteria is 0.005, the difference between two successive page rank of the same node, the current page rank and the updated page rank, if the difference is lesser than 0.005, that is if it is greater than 0.005, it is unacceptable. But if it is lesser than 0.005 difference, absolute difference, then we can say our population has converged, we have reached to the criteria. So in this case, for the iteration number 2, there were many values above 0.005. So fine. Now, as we move towards the iteration number 7, there were few values which was within the threshold, and there were few who was above the threshold. Okay. Then we move to the next iteration. In the next iteration, there left only 3 values which was greater than that threshold of 0.005. All were within the range of 0.004. What does it mean? So if that difference is 0.001, what does it mean? It means that the previous page rank was 0.028183, and now the current page rank is 0.024084. So in that case, the difference between them is 0.004 something. Okay, and if it is beyond within the threshold, that is acceptable. It is lesser than 0.005. The difference is difference is lesser than 0.005, so that means that is acceptable. But there were few page rank for few node number 1, node number A, node number D, and node number F. The page rank of these nodes were not matured or was not converged at that time. So we move to the next iteration number 9, and we can, at that time, we see that, oh, almost all of them has converged except one node, which is node number G. Okay, so that means we move to the next iteration, sorry. In this iteration, the population, the page rank was updated, and all the values of absolute difference between the previous page rank and the current page rank was below threshold of 0.005. So this can be our termination criteria, and this can be the final page rank of the graph. So these are the different values. Okay, and you can see that they can, based on that rank, the nodes can be arranged. Okay, but so I can terminate the algorithm at iteration number 10, And if my criteria is 0.005, 0.005 is acceptable. If I make my convergence criteria a bit stricter, means 0.001, okay, if I want that every value should be lesser than 0.001, then I think I'll have to check for uh, the iteration where it converge. Okay, so let me
Sir,
check.
one question here.
G.
So what is the meaning here or significance here that the criteria which we are choosing here 0.005 and how to choose that criteria actually?
Choice is yours.
I mean, so what is the significance here? I didn't get that.
Let me know. Hmm. Now, if I want, if I have changed my criteria to be 0.001, so initially my significance alpha is 0.005. It is almost the same as of significance level which you have seen in your ISM. Okay, so if my alpha is 0.005, what does it mean? It means that, okay, I need to have a different color in this case. Highlight the cell which are greater than 0.001, not red. Let's mark it yellow. Okay, top cell lesser than minus 0.001, not red, yellow. ठीक है. Now, if I choose, I'll explain what is. So if I alpha equals to 10, so that means number of iteration I require will be iteration equals to 10. If I choose my alpha to be 0.001, I'll tell you what is the significance of this value of alpha. If I choose my alpha to be 0.001, means I want the difference between two successive page rank of a same node to be lesser than 0.001. Means you can see if the difference is 0.006 in this case, what is the value? The earlier page rank was 0.030,739, and now the page rank is 0.30571. So what is the difference? Difference is of 0.00168. Okay, so that means those two values, successive values, are almost very close, but there's a small difference between them. If that difference is acceptable, the difference between them, absolute difference between them is lesser than 0.001, means the acceptable range I minus 1, sorry, we can say page rank of xi minus 1 and page rank of xi, if the difference is the absolute difference between two successive page rank is below alpha, which means that there is a significant difference between successive value. Okay, if I so that means how precise my result is. So if I want my alpha to be 0.001, or ultimately in that sense, if I can say 0.001 means 5%, 0.5% error of margin. Error margin is 0.5%. 0.1% error of margin. If I say 0.1% of error of margin means 99.9% accuracy. Here 99.5% accuracy. Ultimately, it is accuracy, na? How accurate your results are. What is the difference? So if I want more, lesser alpha means more accuracy, means we can say the error margin is less. So that means I'll have to iterate more. Okay. So if I want that difference to be 0.001, 99.9% accuracy, then I'll have to move towards iteration number 5, because iteration number 16 gives me a values of a desired range. You can see the difference between two successive values are almost same. Okay, with a very minute difference between them. And what is the difference? Difference between them is something like this: 0.00001, 0.000257, 0.0000325, and so on. A total, or I can have a total cumulative error also. So cumulative error is 0.002579. If it is acceptable, then I'll have to perform, I'll have to execute this algorithm till iteration 16. Okay, but if I want a 0%, 100% accurate result, means the population is 100% converge, then in that case I will have to execute the algorithm till iteration number 37, because iteration number 38 will give me the same value with the 0% error in the value. Okay, so you can just have a look. Means difference to that decimal place.
Yeah, but
So,
it depends on the decimal place also, right? How many decimal places are we taking?
so it is user defined how accurate, matlab to what extent I want an accuracy. What is my error margin? What is my matlab acceptance range? So if I want alpha to be exactly 0, then I'll have to iterate this algorithm till 38 iteration. Clear?
Yeah, if we take the decimal places up to 10, right? Still we have this the difference if we move to 38 iteration also, right?
No, iteration up to 10%. 10 matlab 0.1. If I alpha, if I consider 2.1, 0.1 na.
No, I mean to say that they depend on the decimal places, right? So as of now, we
हाँ,
are taking 5 decimal, uh,
decimal place.
in counts, right? So if we
हाँ,
take more, right, the iteration will increase.
iteration will be, because for more accuracy, you matlab accuracy cost computations. If you want more accurate result, then you'll have to compute more.
Mhm.
Clear?
Sure. Yeah.
I hope the convergence and all have been cleared. So I will upload this PPT, this Excel sheet again. Okay. We can have a power method also, matrix method. So in spite of in spite of working on an adjacency matrix, what we can do, we can embed the same information into the matrix itself. Okay. So by 2 means, what will be the proportion to be passed? 0.5. So 0.5 to B, 0.5 to C, 0.5 to D, and so on, whatever it be. Okay, so we can have, but the situation will remain the same. Only the computational method have changed, but the situation will remain the same. Okay. So based on that rank, like a pie chart, based on those values, I can have a site. I can have circles of various radius or various diameters. Okay, based on those values, proportional values. Okay, I think that's clear. Pie chart based proportionally, I can have a different nodes, and so that means I can have a visualization. So just by looking at the graph, I can say, oh, that means C and G has the highest rank. So C has the highest rank, then G, then E, then D, then F, then B, then A. Okay, so just a ranking mechanism. The another way how, so that was all in the page rank. And how how others are connected to you. So this, till that point, we were taking care of the in neighbors, how others are connected to you. Now, if I have to find out the centrality measures in terms of how you are connected to others, means your outgoing neighbors of yours. Till now, we were taking care of incoming neighbors. Now, if I have to compute the same thing based on the outgoing neighbors of each node, then we have a different centrality measures. The basic one is the betweenness centrality. Okay, so betweenness centrality means if I do have few nodes, a source and a target, okay, and this is my node on which I'm working with. So a betweenness centrality will be the value. So suppose there may be multiple paths available from S to T. All of them are shortest path. Okay. So I'm talking about, whenever I'm talking about path, it's by default means I'm talking about shortest path. So and in that example we have seen in the previous example, the Excel sheet in which we were discussing all those radius and diameters, I have shown you that there can exist multiple paths, but all of them will be of the same magnitude. So there can be multiple shortest path between one node to another node, between a pair of node. Okay, and in that radius and diameters, we were not bothered about number of shortest path. The only thing we were bothered about was the size of the shortest path. That's all. We were not recording the number of shortest path at that time. But somehow, if we want to include that information also, how many number of shortest paths are there from a pair of node. Okay, so this we call it as shortest path. But some of them will be, so if our in interest node is I, if I'm working on I, how important a node is between, if I want to calculate the betweenness centrality for ith node, then in that case I will be finding out the number of shortest path from all pairs of node that passes through I and that not passes through I. Okay, so betweenness centrality for the ith node will be all the path from sources and vertices, means from all pairs of node, okay, which passes through that node, divided by overall all the path from the sources and destination. So if in this example, how many paths are there from S to T? 1, 2, 3, 4, 5. Among those 5, how many passes through a node Vi? Only 2. So betweenness centrality for Vi will be 2 by 5. So this will give me how important a node is in between the path of all others. So how many shortest path of all pairs of node passes through I? Okay, so that may be considered as some measures in which if there are more number of paths which are passing through I, so that means I may be important to important in terms of SNT. So that means there are more a path passing through I, and there are less paths which are bypassing the I. Okay, so that this importance, this again will give me some measure of importance, and we call it as betweenness centrality. So it will be a ratio of number of shortest path from source to destination of all the nodes that passes through a particular node. So that is specific to one node. Specific to each node. So that means it will be the betweenness centrality will again be a vector, same like eigenvalue centrality, but here I'm bothered about how many times all the paths are being passed through that node. Okay, divided by the number of shortest path from S to T, and we call it as information pathway. Provided that, so that is summation of all, provided that source is not equals to destination is not equals to Vi. What does it mean? It means that it should be from different nodes. So source and destination should be different. It should not be the case that source to source. If this is S to S, so S to S will not be. S and T, source and destination should be different. This is the interpretation of this sentence, this expression, that's S not equals to T. My source and destination should be altogether different. They cannot be same node. And neither the source nor the destination should be the node on which we are working on. Okay, so if we are trying to find out the centrality vertices, between the centrality for node number 5, for example, so I should not I should not be working on all the path which either starts from 5 or ends at 5. So Vi should not be the source and Vi should not be the destination. And source and destination should also not be same. Okay, so this is the interpretation, mathematical interpretation of this expression. Okay, now if I have to normalize it, what will be the normalizing factor? So the best case for the betweenness centrality will be 1 when all the path, so that means these are the set of S's, these are the set of destination, and all of them passes through a particular node, suppose V7, something like this. If the situation is something like this, they all are passing through a node. In that case, if this is the case, then the betweenness centrality for that node will be 1. That means it is a part of all the paths from one node to another node of a graph. So in this case, it may give you a feeling, oh, that may be a very important node. But actually, graphically, this is the weakest point. Weakest point of the graph.
Sir, one example would be the star, right? I mean, if the central part is the central one, all the path goes through that, right?
So in that case, this is the weakest part of the graph. If that node is being attacked, or if this node is compromised, then that means it will clearly bifurcate the whole graph into two parts, into two pieces. So although initially it was giving me a feeling that, okay, so that means more number of path means more importance, but this may be the weakest part. The alternate way of looking at this betweenness centrality will be, I'm trying to identify the weak points of a graph in terms of connectivity. Connectivity means shortest path. Okay, now, so if this is equals to 1, what does it mean? It means that you choose, if this is an undirected graph, so that's why it is 2 times undirected graph. So if you're choosing any 2 nodes out of n minus 1 node, because 1 is this. Okay, so how many, if my graph contains n node, and if this is my if this is a node on which I'm working, so that means how many nodes are left? The nodes are left as n minus 1. So n minus 1 choose 2. As this is undirected, so double. This will be somehow, it will be equal into n into n minus, sorry, n minus 1 into n minus 2. So this is the normalizing value, normalizing factor for the betweenness centrality. So CB norm will be CB VI divided by 2 twice of n minus 1 choose 2. So one example, if this is my graph, so betweenness centrality for all the pendant, there's one statement. Betweenness centrality of all pendant vertices will be 0. The reason being is, if this is my pendant vertex, then obviously all the path from the rest of the graph should not be passing through V1. It should not be the case that most of those paths are this. It can be ignored. Why I'm extending my path? The shortest path would be this. This wouldn't be the shortest path then. And whenever I'm talking about the path, by default, it means shortest path. So that means if my graph contains a number of pendant vertices, hanging nodes, all the hanging nodes will have a between centrality equals to 0. I need not to find out the between centrality for those set of nodes. Okay, but for the others, I'll have to find out the between centrality for 2, 3, 4, and 5. So what should be the between centrality for 2? So between centrality for node 2, it will be twice, as this is an undirected graph, so that's why it is twice. Now, if I'm doing it for 2, I'll have to do it for all other pairs. So if my pair is V1 and V3, how many shortest paths are there from V1 to V3? There's only one. And in how many paths V1 is playing its role? 1. So that's why it is 1 number of shortest path passing through V2 divided by total number of shortest path between V1 and V3. So this is 1 by 1. Done. So one pair of node. I'll have to do it for all pairs. So V1 to V2, sorry, V1 to V3. Oh, why I can't choose V1 to V2? Because as per the statement, S should not be equals to T, should not be equals to Vi. So no V1 to V2, V1 to V3, then V1 to V4. How many paths are there? Or there's only one. And how in which how many V2 plays a role? 1. So that is again 1 by 1. Okay, fine. Now V1 to V5, V1 to V5, there exists 2 shortest path, and both of them passes through V2. So that's why 2 by 2. Okay, so V1 is done, V3 is done. ठीक है, V1 is done. Fine. अब अभी तो V1 ही हुआ है. I cannot take V2. Fine. Now V3. Now for all pairs from V3. So V3 to V1 is already done. So that's why it is 2. So I cannot take V3 to V1 because I have already found it out V1 to V3. V1 to V2 I cannot take. Like, sorry. So S should not be equals to T, should not be equals to Vi. And currently I'm working on V2. So V1 to V3 we are done. So V1 is done. If I'm now working on V3, so V1, V3 to V4, how many shortest paths are there? 2, and one of them is passing through V2. So that is why it is 1 by 2. Fine. V1 to V3 to V5, how many shortest path is there? 1. And among them, how many passes through V2? 0. So that's why it is 0. So actually it is not 0, it is 0 by 1. Denominator is still non-zero. What is the denominator as per the expression? Denominator is total number of shortest path between those pair of node. So if my pair of node is V3 and V5, how many shortest path is there? 1. How many passing through V2? 0. So that's why it is 0 by 1. So I'm done with this. Now my node to work on is V4. So V4 to V1 already done. V4 to V2 I cannot take. V4 to V3 already done when we were finding out V3 to V4. Okay. So the node which is done left is V5. So V4 to V5, yes, there exists a shortest path. But out of those paths, how many goes through V2? 0. So that's why it is 0 by 1. Okay. So 1 by 1 means 1, 1 plus 1, 2, plus 1, 3, 3.5. 3.5 into 2 comes out to be 7. So 7 is the betweenness centrality for node number 2. Okay. Similarly, I'll have to find out for V3. So if V3 is my node of important or node of target, so V3 to V1, 1 by 1. Okay. Then V3 if this is V3 is my target, then V1 to V2, there exists a shortest path. So again, that is V1 to V2, it is 0 by 1. V1 to V4, there exists a one path only, so that's why 0 by 1. Then V1 to V5, there exists two. How many passes through V3? 1. So that's why it is 1 by 2. Then V2 to V4, there exists only 1. Then V2 to V5, there exists 2, and one of them passes through V3. So that's why it is 1 by 2. And then V4 to V5. How many? 1. So again, 0 by 1. So 0, 0, 0.5, 0.5, 1. 1 into 2 will be 2. So betweenness centrality for node number V3 will be 2. Similarly, if I'm talking about V5, if V5 is my interest, so V1 to V2, 1, 0 by 1. V1 to V3, 0 by 1. V1 to V4, 0 by 1. Then V1 to V5, if my target is V5, fine. So V1 to V5 I cannot check. So V1 to V2 I have checked. V1 to V3 I have checked. V1 to V4 I have checked. Okay, fine. Now V2. So V2 to V3, 1, 0 by 1. V2 to V4, 0 by 1. So I'm done. I cannot take V2 to V5 because of this condition. Okay, so V1 is done. V2 is done. Now let me check for V3. So V3, from V3 to V2, 0 by 1. It's already taken. V3, V2. Where it is? Yeah, here it is. So it's already taken. V3 to V4. Yes, V3 to V4. There exists two paths, and one of them passes through V5. And V5 I cannot take, so I'm done. So that is 0, 0, 0, 0, 0 plus 0.5, 0.5 into 2, it will be 1. So betweenness centrality for, and same V4 and V3, V4 and V3 we can calculate. The value is 2. So betweenness centrality for V2 is 7. V3, this is 0. V3 is 2. V4 is again 2. And V5 is 1. So if I arrange them in an order, what is the which is the node having highest betweenness centrality? Node number 2, and betweenness centrality comes out to be 7. So highest betweenness centrality is of V2, which is 7. Ultimately, it will be the weakest point also. If I remove this, the graph will be broken into two parts. One part contain V1 and another part contain V3, V4, V5. Clear with this?
Sir, I think there is a in the calculation of CVV3, second term
This one?
here. Yeah, V1 to V4, there are two paths, right? And one is
Let me check.
passing through V1.
Let me check. If I'm talking about V3, so that means this is my node of interest. I'm talking about V3. So node
Right.
passing through V3. If my source is V1 and my destination is V4, sorry, if my destination is V4 How many shortest paths are there? Shortest path. There's only one.
Only one.
Clear? I hope your doubt is clarified now.
Okay. I was considering this also V1, V2, V3, V5, V4.
Fine. But this is not the shortest one. Na? This contain two
Okay.
edges and this contain 1, 2, 3, 4. So this path is not the shortest one. Although it is a path, but it is not the shortest path. The moment I'm talking about the path, path by default here means shortest path.
Okay.
Yeah.
Yeah, clear. Thank you.
So
Any more
one
queries?
query, yeah, generally like what I see is the end nodes will be zero centrality, between us centrality is zero, and the most ones where we have the kind of a splits or clusters, that will be the maximum. Is this what we can infer as well? Mm, well,
Sorry, can you please repeat it?
so my query is like we have the end nodes at between the centrality as zero, and the center middle ones where we have the maximum split, that will be the maximum between the centrality. That is how it will be there always. We can we infer it this way as well?
Um, mm, in that case, if you say the end nodes means the tails, or we can say hanging nodes will have the will have the between the centrality zero. That's correct. Okay, so for them, for them, the statement for hanging nodes, all of them will have a between a centrality of zero. But if you're talking about that key central vertices, means the node which has coming in between means most of those paths are in that case to some extent, yes, because if it is the central vertex, so that means all of the nodes, well, it has a smaller reachability. No, not in that sense. These are two different perspectives. Central node is something in which I'm talking about the shortest path from that node to all the other node of a graph. Okay, so that means that lying in the mid of the graph. And if it is in the mid, then definitely if there's any graph which is in the mid, then that means most of those paths may be passing through them. Is it obvious? Is it a general statement? If my graph is central vertex, then is it necessary that most of those paths will be passing through that node?
If it's like a
Obvious
junction,
answer.
if it
Is
is
it
if
is
it is
it
a,
true always?
may not be, but if it is a, like what I see is like if it is a junction kind of stuff, then it should be
If it is a junction kind of a thing, then in
Or,
that case, yes.
hmm.
or we can say, right, maximum number of nodes with maximum number of neighbors will have the highest centrality.
Not necessary, because I'm not bothered about neighbors. I'm bothered about the shortest path between pairs of nodes. But
That is fine, right?
yes,
Suppose if
uh-huh.
if even for you, I mean V3, right? V3 have two more neighbors, right? Suppose V6 and V7. Then the centrality will increase for V3.
In that case, I think the centrality between a centrality for V3 will be more as comparison to V2.
V2, right?
Somehow,
Sir, here
mm,
another example. Sir, V3, V4, V5 all have neighbor 2, but for V5 it is 1. The value is 1. But whereas V3 and V4 having higher betweenity.
in that case, suppose for example, V3, V4, and V5, all the three nodes have the degree 2. But still,
Correct.
V5 is not that important in terms of path connectivity, whereas V2 and V3 have the same value. But among them, V2 have the highest one, which is equals to 7. Is it, most of the time, the first intuition about all these queries is yes, if the node is almost in the mid, then its between the centrality will be high. But is it always? Most probably yes. Okay, should I move ahead? Is the concept clear? So now in that case, higher the betweenness centrality is, more weaker the point is in the graph. So nodes with the highest betweenness centrality will be the weakest point in the graph, where if you attack, you will decrease the connectivity of the graph. Not necessary that the graph will be disconnected, not always, but it will reduce the connectivity of a graph. That's for sure. In the worst case, it can also make it disconnected, but definitely it will reduce the connectivity of a graph. So if this is the second example, we can come up with certain betweenness centrality and we can link them. Fine. The another centrality measure is in terms of how fast you can reach. Okay, means the size of the shortest path. So we call it as closeness centrality. Okay, so the intuition is that influential or the central nodes can be can quickly reach other nodes. So that means these nodes should have a smaller average shortest path length. Okay, so we have already calculated the average path length, average shortest path length. If you do remember in that Excel sheet of eccentricity, we have calculated the average path length. And among them, whoever has the smallest value will be the closeness, will be the closest node of the graph. So closeness centrality for the ith node will be called as 1 by IVI. And how come the IVI be calculated? It is 1 by n minus 1, sum of all those pairs of node in which Vj not equals to Vi, means the end point of that edge should not be the same node. Means I should not work on a loop. Okay, so that means loop should not exist. Some in that, so 1 by n minus 1 summation of all those length of the path from one node to other node of the graph. So for all i's and j's, provided that both of them are not same, so that means there's no self loop. How can this be calculated? So suppose if I have to find this again is a with respect to each node. So closeness centrality for node v1. Okay, so it is how many nodes are there? 1, 2, 3, 4, 5. So 1 by 5 minus 1, 4. So that's why it is 1 by 4. Now sum of all the path, provided that if I'm working on 1, so 1, the end point should not be, the end point of that path should not be the same node. Means I should not work on the self loop. So v1 to v2, how many shortest, what is the size of the shortest path? The size of the shortest path is 1. v1 to v3, what is the size of the shortest path? 2. v1 to v4, v1 to v4, what is the size of the shortest path? 2. v1 to v5, what is the size of the shortest path? 1, 2, 3. If I would have been considering the number of shortest path, then that would have been v1 to v5, there are 2 shortest path. But I'm not bothered about the number of shortest path. I'm bothered about the number of shortest path. Okay, so that is 1 by n minus 1, 1 by 4 by 1 plus 2 plus 2 plus 3. So it comes out to be 0.5. Similarly, for V2, V2 to V1 1, V2 to V3 1, V2 to V4 1. So V1, V2, V3. Okay. Sorry, not V2. Sorry, my bad. I cannot take it V2. So from V2 to V1, from V2 to V3, from V2 to V4. Just give me a minute. Okay, sorry for that. Okay, fine. So if I'm talking about V2, so V1, V3, V4, and then V5. Similarly, for V4, V1, V2, if it is V3, then V4, or if it is V4, then V3, then V5. No, it is not so. If it is V1, so V2, V5, 1, 1. Sorry. If it is V3 or V4, so V2 and V2 or V5. So V2, V5 has a path length of 2, and then V1
and V4.
and V4. V4 if it is V3, and V3 it is if it is V4. Okay. Similarly for V5, this is V1, V3, V4 has a path length of 1, 1, and then V2, and then V1. So this is how we can find out the betweenness centrality for each node. Okay. And based on that, whoever has the highest one will be considered as the weakest point. So that means V2 will be the weakest point in the graph, having the highest betweenness centrality. Fine. Weakest point in terms of connectivity. So if that node is being removed, the graph will become disconnected, or the connectivity reduces. Weakest in terms of connectivity. So Manoranjan, is that clear?
Yes, sir. Thank you.
Second example. Okay, a comparatively bigger one, but it's easy, doable. Even we can do it for directed graph as well. So if we compare all the three network measures by putting them all together in a matrix form. So we have three centrality values: degree centrality, closeness centrality, and betweenness centrality. Degree centrality talks about the neighbors, incoming neighbors. Closeness centrality talks about how close you are in terms of reachability. And betweenness centrality talks about how important you are in other decisions. Okay, it can be the another perspective now for the betweenness centrality. Okay, if somebody is deciding something, so how important you are in some other decisions. If all those decisions are going through you, so that means you may be important for them. You may be a vidwan, that who want to do something, they just come to you for suggestion, and then they do their activity. Okay, so this may be the another perspective of the betweenness centrality. So how high betweenness means you are we can say suggestion maker or decision maker in all those decisions. Whatever they want to do, that decision or that path will goes through you. Okay, so this is the interpretation of betweenness. Now, what is the physical interpretation for their different values? So either a degree centrality can be high, those centrality measures can be high, or those degree or those centrality measures can be low. Now, what is the interpretation if any node has a high degree but low closeness? So high degree means connectivity. Okay, in terms of connectivity, the connectivity is high, the degree is high, but it is not close. So low closeness means there are multiple shortest path. Okay, so if closeness centrality is high, what does it mean? That most of those path, if I'm talking about V2, so that means most of those path are if closeness centrality is high, so that means this is the smallest. So that means because this is in inverse na. Closeness and why this is inverse. So in that case, closeness centrality is 1 by LE. Okay, so that means if you are close, you are lying at towards the center of the node, so that means you are very close. Then you if the average average path length is smaller, then your closeness centrality will be high. So average path length is smaller means you are lying towards the center of a graph. Okay, so if your path length is smaller, your closeness value will be high. So that means you are close to more and more nodes. If your path length is more, that means you are moving towards the periphery of the graph. You are moving towards the outer layer of the graph. Okay, so in that case, your closeness value will be low. Okay, so high degree, okay, many persons are connected to you, but a low closeness means you are moving towards the you are towards the outer of the graph. So what is the interpretation? Interpretation is node is embedded in a community because of the degree. Okay, so that is a part of some community, but that community itself is far from the network. Okay, you are a king of certain community, but that community is not in the society. Jungle mein ho aap. Okay, so that is the interpretation, that nobody, You are important to your own community only, but your community is not part of the society. Okay, so high degree and low closeness, whereas low degree and high closeness. So although your connectivity is low, but you are a part of many decisions. You are embedding in towards the center of a graph. So that means key nodes are connected to the important or active elders. So that means you are lying towards the center of a graph. Okay. High betweenness and low degree. High betweenness, हाँ, ठीक है. So this we have done high degree, low closeness, and high closeness, low degree. High degree, sorry, high betweenness, low degree. So although you have a low degree, but your betweenness value is high. Okay, so that means although your degree is less, but so in what situation did this happens? Degree is low, but you are participating in most of those paths. So that means you are connected to any of those such nodes. Suppose, for example, if this is the case, this degree is just 2, but you are in a pipeline of the betweenness centrality, means you are in the pipeline of those weakest point, or you are in between that community which have been asked more. Okay, so that means you are very important to the network flow, you are a part of it, but your community itself is low, means your friends or your neighbors are good connected, okay, very well connected across the network, and all of them are, and they are influential. Most of those paths are going through them, and you're not connected to any other, but you have chosen a good friends. Both of them are your friends. Okay. Similarly, high betweenness and low closeness. Okay. So you are lying in between, but you're not towards the center of the graph. Your closeness value is high. Okay. So ego monopolizes the ties from a smaller number of peoples to many other. If I do have a high degree and low betweenness, so high degree, I have a very high degree, but most of those paths are not passing through me. Okay, so that means the communication bypasses that node. So ego connections are redundant. Communication bypasses the node. Although you may be important, you have a high degree, but because of your ego, most of those are bypassing you. They are finding an alternate path rather than approaching you. The another perspective of high closeness and low betweenness. So you are towards the center of a graph, but you're not participating, or you are not part of those decisions. You're not part of those important flows. So what can be the reason? There can be the multiple path in the networks are there. So probably multiple path in the network. Okay. So there are multiple other options available, and the other chooses to use those paths. So ego is near many people, but so are many others. Okay. So that means there are multiple paths available, and all the other person often chooses to ignore you or bypass you. Find an alternate way to find out the to get the work done in terms of connectivity. Okay, so it is till now we were dealing with the individuals. Can I do it for a group? Yes, I can, The only thing is कि earlier, if suppose for example, if I am dealing with a particular graph or a very big size, okay. So group node centrality for this one, all the centrality measures for each and every individual nodes. I can do it for group as well. What can, in that case, what should I be doing? Suppose for example, if I have to focus on these set of nodes, sorry, I consider this as a super node V, okay, and rest as the other nodes. So internal connectivity of these node can be ignored, and I consider this as a super node. And then I can compute all the centrality measures, edge centrality, node centrality, edge betweenness, closeness centrality, and many other things. I can do that. So this can be a group activity as well. So that node will be considered as suppose super node S, and rest of the node will be V minus S. So they all will be a part of V minus S. This is V, and this will be a set of V minus S. So V itself will be a set, okay, and all the other nodes will be a set of V minus S. Same degree centrality again, that for V and from the other V minus S. What I have to normalize, we divide it by mode of V minus S. For the group centrality, sorry, between a centrality as well, we can do that. Here in this case, we will be normalizing it by mod of V minus S by 2. 2 into V minus S, choose 2. Because this S will be considered as one set, one node. Same is the case for group centrality, we can do that. Okay. Now, so this was in terms of connectivity. If we'll have to find out the network measures based on the patterns.
Sir, one quick question.
G.
For that group, no? So can we create a group of vertices which are not connected? Is it connection is connected graphs are vertices are mandatory for group?
Connected vertices means, suppose for example, matlab, if this is my graph, suppose, means in that way, suppose for example, in this way. Now you're saying that this node, and this node can be considered as V. Is it so?
Yeah.
So in that case, this can a choice of nodes, matlab, grouping of nodes is your choice, but it will be a part of a single large graph, na?
Yeah, understood, sir.
So not necessarily, in this case, it might give you an intuition that the nodes along with their neighborhood can be considered as a V. Not necessary. It can be any set. So suppose A, B, and C can be considered as one set. Okay, so this will be my super node V. I will bring them together. I'll have the same some change orientation. I bring them together as I will consider, put them in one set, and rest of those D, E, F, G, H, I, J will be a part of V minus S. D to J, whatever it be, they may be the part of V minus S set. Here.
So here the definition a little bit tricky. It's not very clear. See, it's saying that Vi belongs to V minus S. That means Vi belongs to V but not in S. And Vi is connected to Vj, where Vj belongs to S.
Okay, fine. So degree centrality such that Vi belongs to V minus S, means one of the node belongs to the other set V minus S, such that Vi is connected to Vj. So Vi may be one node from this, okay, and Vj is one node from S. And I'm trying to find out between I and J. So V is connected to Vj in any of those nodes, where Vj belongs to the superset that we have. In this case, sorry, मेरी गलती, मैंने नाम ही गलत लिए हैं. Usually S I have considered in that case, S was considered as a superset. Okay, so the set will be V minus S. Clear now? And V is the all the sets of a graph. A to J. V is the set of all vertices of a graph. So from that, I picked a 3 node which I call it as S. So V minus S means DCD will be VV minus S. Okay, so this may be the correct way. I have used the wrong key terminology or abbreviation, but this is the case. So Vi belongs to V minus S, and Vj belongs to set. So in any node from S, either A or B or C. Is it good now?
Yes, sir. Now it's clear.
So your S is R group and V minus S is your outside group.
Yes,
This
of
is
course,
what.
no.
Yeah, okay.
S is the set which we have clubbed together as one node. So S is the super node.
Got it. Thanks.
User defined. Fine. So it can be a group activity as well. So if I consider this, if I consider a subgraph out of the main graph, all the network measures are also applicable for that subgraph as well. That subgraph will be considered as a super node, one bigger node. So we can find all the degrees or the net we can say network measures for him also, for that subgraph as well. Now the next way of looking at the network measures in terms of patterns. So transitivity, reciprocity, status, and balance, which are very well used for the recommendation system. Okay, patterns. If A is related to B, B is related to C, then can A be related to C as well? So that means if A is the friend of B, B is the friend of C, then can A be recommended as a friend of C? Yes. If that relation holds, then in that case, yes or no. So something related in terms of patterns or recommendation system. Okay. So if A is related to B and B is related to C, this implies that A can be related to C. This is a very well transitive relation which has been proved in mathematics. But if I'm dealing in terms of directed graph, so V1 has a friendship with V2, V2 has a friendship with V3, means it should not be friendship, it is a known. So V1 knows V2, V2 knows V3. Okay, then in that case, V1 knows V2 and V2 knows V3. नहीं, knows में नहीं आएगा. V1 introduced someone to V2, then V2 introduced someone to V3. No, not introduce also. It can be a friend also. Okay, fine. So if this is the case, now the question arises: what should be, if this is a directed graph? Then what should be the direction? Whether the direction should be like this or the direction should be like this. So that depends upon the scenario. What should be the direction of the new edge which has been recommended? So this can also be used as an edge prediction or link prediction mechanism. So in social network, transitivity is when friend of a friend is my friend. So transitivity in a social network leads to a denser graph. So if the transitivity relation holds or it has been used as a recommendation system, then it leads to the matlab it results in a longer sorry, not longer, denser connectivity of the network, friends network among themselves. So if that network become very dense, it may leads to a complete graph, but this is hypothetical. It may not be possible. We can determine how close a graph are to the complete graph by measuring the transitivity. If transitivity is high, then that means the graph is almost moving towards the complete. Now, what is a transitivity means? If you think we were talking about clustering coefficient, in the clustering coefficient we were talking about triangles, and this is what, again, a triangle only, no? So more number of triangles, more dense connectivity, more the graph tends to be complete or click. So I think if this is the case, then I think we can revisit the clustering coefficient.
I have just a small query on the previous slide, especially with the direction of this stuff. So we are seeing A is related to B is related to C, but then we have direction as well, and the relation like related to is generally not directional. It is like bidirectional, and now we are representing it by the direction. So that's why it's like I'm just a bit confused in this.
Yeah, no issue, no issue. But the thing is, if you think if you can understand this in terms of biconnectivity, then that's okay.
Biconnectivity is okay, and then you are asking question like whether CRA or ARC, and that's why the query came up.
नहीं ठीक है. The thing is कि I thought of answering this, but unfortunately I was not able to frame a particular example where CRA and ARC was different to each other. So that's why I skip it. I thought of explaining that scenario and then coming up with an example, but unfortunately at the runtime I was not able to frame the example in which those two relations are different. So that's why I thought of skipping it. But if it is bidirectional, it doesn't have any problem.
Yeah, that's
Either
fine.
ARC or CR, fine. But if specifically, but the thing is to be unfortunately, I was trying to explain you in terms of a single direction, unidirectional edges, but unfortunately, example doesn't clicks into my mind at that time. Not even now. Also, I'm not able to think a particular example where CRA should be different from ARC. A is the brother of B, B is the brother of C, then that brother of kind B.
So
Kind.
divisible is also a
A
example.
is divisible by B, B is divisible by C, then in that case, A will be divisible by C. But C will be divisible, A is divisible by B, but B is a multiple of A. Na?
Yeah.
So in that case,
Divisible.
if A are B and B are A, the reversible relations doesn't exist. So in a friends, A to B and B to A are the same. Fine, that's good. Thank you. Divisible. So A is divisible by B, but B is a multiplier of A. So in that case, A to B and B to A are not same. So in that case, what should be the direction? That depends upon the type of relation we are working on. That is specific to the relation on which we are working. What kind of edges we are taking. Thank you. Thanks for that example. I was trying to figure out something, but I was not able to figure out that different between both the relations. So thank you. Now let us move back again to the clustering. So clustering coefficient with the same thing. Okay. Triplet. There we were talking about the triplet. So triplet means three nodes connected together. Ultimately, what is it? Paths of length 2. So closed path of length 2 means this. Overall, all the paths of length 2 means this one. Okay. Here, if you do remember, we have multiplied 3 into number of triangles. If that orientation matters, if the orientation doesn't matters to me, So the factor can be 6. So here number of triangles into 6 means again 3 in 1, A to B, B to C, matlab, A to B, A B C, B C A, and then C A B. Okay, so that's why it was 3. If even I'm not bothered about the orientation, then there will be 6 possibility: A B C, B C A, C A B, then reverse. Nahin, A B C, B C A, then nahin, A B C, B C A, and then C A B. Ha, theek hai. Now then the another 3 different examples will be the reverse. CBA. So earlier the orientation was this. Now the orientation is this. So CBA, BAC, and CBA. And they all are different. So that's why if the orientation doesn't matter, so that's why the multiplying factor can be 6 also. So in either way, in both the ways, the clustering coefficient have the same meaning. Ultimately, number of triangles divided by number of paths. If I'm talking about orientation, one orientation clockwise and anti-clockwise, then 3. If I'm not bothered about orientation as well, then the multiplying factor will be 6. But this is just a constant. Okay. So clustering coefficient and triples, this is the same thing which I think I've closed. So if this is the example, I think this is the same example which I think unfortunately no. I think this was the example that we have solved. Yeah, if this is our case, so number of triangles into number of connected triples. Now look, so that was global clustering coefficient, and in the slide we have not focused more on local clustering coefficient. The local clustering coefficient measures the transitivity at the node level. So it is commonly employed for the undirected graph and computes how strongly neighbors of a node V are themselves connected. So CVI will be the number of pairs of node of VI that are connected to each other divided by total number of pairs. If this is in an undirected graph, the denominator will be degree. So n degree into di by d minus 1 by 2. If it is directed graph, then it will be di into di minus 1. So what does they provide? The local clustering coefficient provides what all are the structural holes, if there is any structural hole into the graph as well. So if this is my case, then the local clustering coefficient can suggest the structural holes into the graph. Okay, fine. The thin line, okay. So this is the case when the clustering coefficient value is 1. So thin line depicts the connection to a graph. Dashed line are the missing link among the neighbors, and solid line indicates the connected neighbors. So if this is my graph, then in this case, the clustering coefficient of V1 will be equals to 1. Clustering coefficient of V1 in this case, it will be 1 by 3. How many triangles it has been participating it. Okay. And in this case, when there's no direct edge or missing link, then the clustering coefficient, local clustering coefficient of V1 will be equals to 0. So how the neighbors by themselves are being connected. Okay. So ultimately, the intuition is this. I'm just trying to figure out by this clustering coefficient, local clustering coefficient, I'm trying to figure out how neighbors are connected by themselves. I'm not talking about V1. I'm talking about the neighbors of V1. So in this case, who all are the neighbors of V1? V2, V3, and V4 are the neighbors of V1, and they themselves are connected in the form of a triangle. So that means they themselves are very well connected. They themselves are a part of the cluster or a triangle. So that's why the clustering coefficient, local clustering coefficient is 1. In this case, sorry, V2, V3, V4. So how many neighbors are there for V1, V2, V3, V4? 3. And among them, how many are connected together? There's only one pair of node which has been connected. So that means the local clustering coefficient for V1 is 1 by 3. Okay. In this case, V2, V3, V4 are the 3 neighbors of V1, and there is no connection between the neighbors. So that means neighbors by themselves are not connected. So how many neighbors are there? 3. How many connections? How many connected neighbors are there? 0. So that's why the local clustering coefficient of V1 will be equals to 0. ठीक है?
So it's just like how good my neighbors are connected. That's what. Yeah. Okay.
So in that case, I'm not bothered about my connectivity. I am connected, so I'm not bothered about my connectivity. I'm bothered about how connected my neighbors are.
Got it. Thanks.
So this is a different perspective of looking at the connectivity. The another measures for network, we can say, another network measures in terms of balance. Okay, so in terms of consistency into the relationship. So the social balancing theory, in this case, the consistency in a friends or a foul relation among those individuals. Okay, so this relationship is consistent when if all the 4 condition holds. Friend of my friend is my friend. Friend of my enemy is my enemy. That's also a valid one. Enemy of my enemy. So enemy of my enemy will be my friend. That's also hold. And enemy of my friend. Enemy of my friend, mere dost ka dushman, mera dushman. So enemy of my friend is my enemy. So all the if all the 4 rules hold in the social balance, in the social networking, then in that case, that will be that relationship will be consistent. Now, for example, I have a friend, suppose I'm A, I have a friend B, okay, and I have an enemy as well, C. So C is my enemy, B is my friend, but they also are friend together. Is this a consistence? No, that means A is my friend, B is my friend, but B is also a friend of my enemy. So that means whatever I say to him about C will directly be conveyed to C because he will be the mantra of this case. So that means this relationship will not be consistent. Okay, now how to check these kind of consistencies? So in the network, we can assign the positive friendship and friendship as a positive weight, and negative means negative edges as an enemy by the negative edges. Okay. Now, if my triangle, if my relation will be balanced, if the triangle is the sum of all those values are sum of all those weights comes out to be positive. So in a relation, in that connectivity, positive for friendship, negative for enemy. Okay. And if I have to deal with 3 IJK, the reason I have already explained you why I'm bothered most about the triangle, because triangles are the smallest complete graph, and it they are the basic building blocks towards the higher order complete graph. Okay. So this triangle of the node ijk is balanced if and only if product of all the weights comes out to be positive. What does it mean? So that means V1 is a friend of V3, V3 is a friend of V2, and V2 is a friend of V1. If this relation holds, so that means plus into plus into plus. Wij into Wkj into Wki. If product of all the three weights is greater than 0, so that means this will be balanced. Fine. V1 and V3 are friends. V3 and V2 are enemies. So in that case, V1 and not so. For example, V1 and V3 are friends. V3 and V2 are enemies, and V1 and V2 are also enemies. Okay. So is this relationship balanced? So let me check. Plus into minus minus, minus into plus plus. So that means it is again positive value. Okay. So that means this is again a balanced one. V1 has two enemies, V1, V2 and V3. So these two enemies can be friends together. Let me check if this relation holds. So minus plus minus into plus minus into minus plus. So that's again a positive one. V1 and V3 are enemies. V3 and V2 are enemies. So V1 and V2 can be friends. That's again a plus. So if the multiplication of all the edges of a triangle comes out to be positive, I can say that relationship is consistent. If it is positive, sorry, if it is negative, then the relation will be unbalanced. So for any cycle, if the multiplication of edges values become positive, then the cycle is socially balanced, or else the relation is unbalanced. It will not hold. It is not a trustworthy relationship. So status in the social networking shows how prestigious an individual is ranked within the society. Whereas the social status theory tells me how consistent an individual are in assigning status to their neighbors. So if X has a higher status than Y, Y has a higher status than Z, then X should have a higher status than Z. This also should hold. Okay. So a directed plus edge from a node X to node Y shows that X has a higher status than Y, and negative shows a lower status. So if V1 has a higher status than V2 and V2 has a higher status than V3, so that means V1 will be at a higher status than V3, or it can be age group also. So V1 is elder than V2, V2 is elder than V3, then obviously V1 is elder than V3. Okay, not of same age. If twins are born at the same day is being ignored, then even the elder relationship is a stable configuration. Okay, it cannot be. Okay, V1 is elder than V2. So if plus means elder and sorry, plus if in this case negative was elder and suppose positive is younger. So V1 is younger than V2, V2 is younger than V3, but V1 is elder than V3. Is it so? What I have said, sorry, I have confused. I have confused myself. If this is younger, so that means V1 is younger than V2. So that means V2 is older. And this is younger. Okay. Let me check. I have confused myself only. V2 is younger than V3. So that means even younger. So this is older. No, uh, no, it cannot be. V1 V1 is younger than V2. So that means V1 is older than V2. Okay. V2 is younger than V3. So that means V2 is younger than V2. क्या बोल रहा हूँ नहीं यहाँ पर वो younger older नहीं आएगा because I'm not strictly younger मैं भी strictly younger मैं भी कह सकता हूँ कि suppose V1 is older than V2 so that means V2 is younger. V1 is younger than V2 नहीं यार फिर older क्या होगा? Sorry, should I take that example or should I ignore it? Because I think I have made some wrong statement and I have confused myself by taking a wrong relationship of being younger. And this is older. Okay. So V1 is younger than V2. V1 is younger. So that means V2 is older. So suppose if he is of 21, V1 is younger than V2. So that means it will be at least greater than 21. Now V2 is younger than V3. So that means if it is 22, I consider this as a 20, 22 or 23. Age group of this is this. Then V1 is younger than V2. Okay. So in that case, that if this is my younger relationship, then this will be an unstable configuration because if this is of 21 and this is of 23, so it should be something like this. V3 is older than or elder than V2, V1. So if this plus is younger and minus is older, this configuration is unstable. Correct.
Sir, it is stable only, right? Greater than greater
It is
than
unstable.
because
If
V1 is the way V1 is related to V2, the same way V1 is related to V3. So it is stable only, right? So
no,
we said
that is
that
triangle. If I'm talking about this triangle,
huh? So
so if
we
plus
told that
is the younger relationship, plus is the younger relationship, so
correct.
negative will be the elder relationship, older
Correct.
relationship.
So V2 is older than V1. That's why there is a plus. Correct.
So suppose, for
Now
example, his age is 22.
22, right? Now V2 is V2 and V3 is plus. So that means V3 is 23, right?
V2 is
So
younger than V3. Suppose 23.
so V1 is now 21 and V3 is 23. So definitely plus will be there itself. No.
Now, in that case, if that relationship would have been plus, then this will be stable. V1
Correct.
is
But
younger than V3. That's correct. Okay. But if my relationship is negative, means older. So in that case, V1 is younger than V3, whereas this relationship states that V1 is older than V3, which is not correct.
okay.
Initially, I confused myself. Then I think I have confused you. So if this is the case, then you can ignore this example of younger and being older.
The
Um, uh,
negative sign made it unstable. If it turned positive, it was fine.
ah,
Yeah, then it would stable. Yeah, that
ah.
is how.
So in that case, if that as in this example of this slide, if positive is the direct edge means higher status, so negative edge means lower status economically or so socially. Then also this relationship will be unstable. Means doesn't exist, not a valid one. Okay, if it is confused, it is not that much important. It just gives us whether that recommendation system will be stable or not. Whether he will accepts the um, a friendship request or not. Now, the most, or we can say not most, but the important, we have reached to an important part of the graph network measures. We call it as similarity. So how similar two nodes are in a network. Now there are two different ways of calculating the similarity. One is structural equivalence and the other is regular equivalence. There's a difference between them. Let us first of all talk about the structural. Now again, this similarity is nothing. It will be somehow based from the connectivity. We have to come up with a numerical value associated with each node of a graph. Okay, so that means this similarity again will be a matrix of order n cross n. Somehow we have to compute the numerical values, which gives me that what is the extent of similarity between two nodes of a graph. So to what extent A is similar to B? To what extent node A is similar to node C? To what extent the node A is similar to D? Okay, now this to what extent is a tricky part. What is my criteria for finding out similarity? Is it based on the network himself? Okay, based on the network, based on the neighborhood. Okay, or this is slightly tricky. We call it as regular equivalence. Okay, so I think I have given you an example in the last session. In the recommendation in the e-commerce site or in a Netflix and all, based on your activity, the algorithm has come up with certain some value associated with you. So based on that, they will recommend you the new movies or new videos, whatever it be, because on an OTT platform, thousands of movies are released or added into the portal daily. Okay, but all those 1,000 movies are not recommended to me. I will not see the list of all those thousand movies which are newly added into the portal. No, only those movies are recommended to me which are either based on the interest, based on the detail which I have filled. If I'm an Indian, then obviously most of the time I will be liking the Indian movies. And Hollywood dubbed in Hindi or thriller movies or romantic movies, whatever it be, I filled up, I put up some check boxes. So those check boxes will be used to filter out the list for those movies which can be recommended to me. And that too, not all, only some of them which are being ranked higher based on my viewing history. If I viewed certain type of movies and even the habit, if I do have a habit of watching the movie on the day it was released, first day, first show, something like this, then the criteria for recommendation will be slightly different. If based on certain, there are some movies which there are many others. So there are some movies which I start viewing but have never completed. So that means, and even the portal also records each and every day how many times I have resumed the movie but I have not completed it. So that means those type of movies are not of my interest. I still thought of viewing that movie, but every time I sit, okay, let's finish that movie. But after viewing 5 minutes or 10 minutes, I loses the interest. Oh, the movie is boring. Let's not what, let's search for the another one. So those kind of movies will not be recommended to me because they are not being completely viewed. So there are many other criteria. So these things, these details, we can say about the neighborhood, about your own activity, about your own attributes. So that type of similarities we call it as structural equivalence. Like-minded peoples and all. Okay, based on your neighbors. The regular equivalence is something different. You might have encountered the same statement which I have made earlier. The person like you have watched this movie. So that you means, suppose for example, that the name is hidden, but if he is recommending me some movie by stating that person like you, so me and that person might not be connected together. We might not have even watched the common movies as well. We might not be from the same geographic location as well, but our viewing interest may be same. So that means our neighborhood is almost same. We are, even though our neighborhood may not also be connected together, but my neighborhood means my attributes and his attributes, his neighbor, is almost of the similar type or similar structure. They may not be connected. I may not be connected to their neighbors. Okay, I may not be connected to him. I may not be connected to his neighbors, or neither his neighbors are connected to my neighbors. But both the neighbors have similar structure. So that type of equivalence is called as regular equivalence. So structural equivalence, we look at the neighborhood shared by the two nodes. Size of this shared neighborhood defines how similar those two neighbors are. Two brothers have in common: sisters, mothers, fathers, grandfather, and so on. So this shows that they are similar. So two random males or female individuals do not have much in common and are called as dissimilar. Okay, so that means if there is no connectivity between them, they will be considered as dissimilar. So this is the structural equivalence. So first of all, we'll talk about more on the structural equivalence, means based on the neighborhood only. And what is my criteria? Common neighbors. So more common neighbors, more similar thing. Less common neighbors, less similar thing. No common neighbor, no similarity. So this is simply and flat way of looking at the similarity in terms of structural. So there are many criteria for structural equivalence. One of them is vertex similarity. So how similar two vertices are, Vi and Vj. So that will be equals to intersection of their neighborhood. So this set contains the neighborhood of I, and this set contains the neighborhood of J. And intersection means common neighbors. Okay, so this we call it as vertex similarity. So we'll have to normalize it. Obviously, every time we'll have to normalize it. So if we normalize the common neighbors by set of all neighbors, Ni union Nj, matlab Nvi union Nvj. So if I normalize the common neighbors by all the neighbors, union of set means all the neighbors, then that type of similarity is called as Jaccard similarity. Whereas if I normalize it by the product of their individual neighborhood size, so this is the neighborhood size of Vi and this is the neighborhood size of Vj, and I take a product of them and then multiply them together and then take a square root. Okay, so that type of similarity will be called as cosine similarity. So what is the difference between the Jaccard similarity and cosine similarity? Jaccard similarity is the normalizing factor is the set of all neighbors, whereas cosine similarity, the normalizing factor is their size of their individual neighbors. Okay, what the difference? Set of all common neighbors, set of all the neighbors, fine. And here cosine similarity is the product of their size of their individual neighborhood. So that's obvious that neighborhood of V exclude the node itself. A person cannot be a neighbor of himself. Okay. Now again, make it a bit more complex. By default, so even though I have not here, I have not mentioned about the hop neighbors. If I want to make it complex, I can talk about hop neighborhood. Okay, one hop neighborhood, two hop neighborhood, three hop neighborhood, and four hop neighborhood. So in that case, if I vary my h, the size of the neighborhood will vary, the coverage will vary, but it will again give me some sense of similarity in terms of neighborhood, direct neighbors, then indirect neighbors, and so on. Most probably we doesn't do much, not greater than 3. Okay, for most of those calculations here, by default, if nothing is being mentioned, they are the direct neighbors. So if nothing is being mentioned, we are bothered about direct neighbors only. But if you want to make the thing complex, but visualize in a different perspective, then we can also include the hop neighbors as well. Clear? So if this is the case, if this is the graph, if I have to find out the Jaccard similarity and cosine similarity for two nodes, that is that is with respect to the specific nodes as well. Those V's, VI's and VJ's. Okay. So if I'm specifically want to find out for V2 and V5, then what all are the common neighbors? V2 and V5, the common neighbors is 1, V3. So V1, 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 V3, V4, intersection V3, V1, V6. So it will be V3 divided by 1, 2, 3, 4, union of all those. So 1, 2, 3, 4. So these are the neighbors of V2 and these are the neighbors of V5. So V1, V3, V4, V6. V1, V3, V4, V6. One by 4 equals to 0.25. Cosine similarity, here again, common neighbor is still V3. Okay, so if I write it in that way, so 1 divided by 3 into 2. So 1 by square root of 6 comes out to be 0.4. Okay, is that clear? 340. Oh, sorry. Okay, so okay, so that means that is clear. The second thing is I'll finish it in a minute. Regular equivalence means I'm talking about the neighborhood. Okay, so that means those neighbors, regular, okay, no issue. Should I? This requires some conceptual. I may require around 5 minutes. Okay, so I'll stop over here. Hardly, I may require 5-10 minutes more to explain this regular equals, but later on, no issue. So I'll stop over here. Quickly in the next class, I will talk about regular equivalence and then we'll move forward.
Okay, just a small query on structure equivalence. I want to just thinking of the significance of Jaccard and the other one. Like, what is best, Jaccard versus cosine, and
Okay, right.
Mm,
The moment in Jacquard similarity, the numerator part is same. So that means common neighbor.
Yeah.
The only difference is
That
by what factor I'm normalizing it. So if I'm normalizing it by the set of all the neighbors,
is the
this
whole
is the
set.
set of all the neighbors. Okay, so that will be the Jacquard similarity. If I'm normalizing it by their size of their individual size of the neighborhood size of their individual name. What should I say? Product of their size of the
Number.
neighborhood.
Yeah. Progressive.
Size of the neighborhood individual. Okay, and then I'm taking a square root. That means it may be possible that this set may become bigger. So in
Yeah.
order to reduce it, so if so suppose 2 into 2, 4, and then take a square root, it again will come back to 2. So that means I'm making the thing bigger, and then what is the physical interpretation of square rooting of anything? If I take a square root of anything, means I am dividing it exactly into two multipliers. If suppose if it is 2 and 2, what means? It means that if there is any I which is square root of x, what does it mean? It means that it have been if it have been divided into two identical part, that then only it will be the square root of that will be I now. If it is 2, so that means square root of 2 into 2, two almost identical part, means I have divided it into two exactly two equal part and then take a square root. So that will be the normalizing factor. Somehow I'll have to convert it by normalize. Why? What is the basic criteria for normalizing it? Basic criteria is I'll have to put them in a range. By normalizing it, I'm putting the values into the range such that it doesn't grow bigger beyond the range. Okay, so
Okay. So as per my understanding, it is like one is for the size, cosine one, of course, that we are more giving more importance to the size of it, the neighbors, and the other one is maybe the whole neighbor kind of a union overlap.
sorry, I was not able to hear it. What was your query?
No, no. My inference is that cosine one is that we are focusing more on the size of the neighborhood, and the first one that we are Jacquard is more on the what you call
Size of the complete set.
yeah, cosine is for size of the complete set, and Jacquard is for the what you call
No, no.
overlap union, something like that.
That is the size of the complete set of neighbors.
Yep.
It may be common neighbors. It may be their individual neighbors.
Yeah,
Whereas cosine is the product of their individual size of the neighborhood.
got it. Thanks. So thanks. Maybe I'll read more and then I'll get some more focus.
Okay. So I'm stopping the recording.